Take a standard 28 by 28 pixel image of a handwritten digit. To a computer, this grid is a single data point in a 784-dimensional space. Every pixel acts as its own independent geometric axis. Working at this scale introduces severe friction. A 784-dimensional space creates mathematical intractability. Distances between points distort, computations become prohibitively expensive, and visualizing the data is impossible. High-dimensional data contains inherent shortcuts. An image is overcomplete. Adjacent pixels are highly correlated. If one is black, its neighbor is likely black as well. Because of these correlations, the vast majority of those 784 dimensions are redundant. This redundancy allows us to perform linear dimensionality reduction. The objective is to search through the noise and extract a latent, lower-dimensional code hidden inside. Principal component analysis, or PCA, solves this exact problem. By analyzing the covariance of the data, PCA mathematically deduces the absolute optimal axes of compression. This mathematical bridge takes the sprawling, high-dimensional reality of raw inputs and compresses it down into a tight, computationally efficient format we can actually analyze. This chart shows the result of applying PCA to high-dimensional images, mapping the 784-dimensional MNIST space into a two-dimensional structure. Look closely at the clustering on the right. These clusters correspond to handwritten zeros, proving the algorithm captured the inherent structural information. Out of 784 possible dimensions, how exactly did the algorithm calculate these specific projection axes? This geometric structure is mathematically derived directly from the variance of the data itself. We frame PCA as a linear autoencoder. An original data vector X passes through an encoder matrix, B transpose, mapping down into a compressed code vector Z. The process is reversible. The code Z passes through a decoder matrix B, producing the reconstructed vector, X tilde. The properties of this matrix B are strict. Its columns must form an orthonormal basis, meaning they establish a set of perpendicular, unit-length axes that span our new lower-dimensional subspace. We have to choose a specific orthonormal basis that minimizes the mathematical difference between the original X and the reconstructed X tilde, ensuring the least amount of information is lost during compression. By structuring PCA as an encoder-decoder pair, the abstract task of finding patterns becomes a rigorous mathematical search for the absolute optimal linear mapping. In this geometric space, we measure information content by observing the spatial spread, or the variance, of the dataset. To compress a 2D data cloud into a single dimension, we project points onto a lower line, keeping them maximally spread. An arbitrary axis compresses points, destroying distinction. But rotating the line to align with the longest spread preserves maximum variance. Assuming the data is centered at 0, this spread is defined entirely by the data covariance matrix, S. This gives us a precise mathematical objective. We need to find the specific projection vector, B sub 1, that maximizes the quadratic form, B sub 1 transpose times S times B sub 1. We must also enforce a unit vector constraint, setting the length of B sub 1 precisely to 1. Without this restriction, you could artificially inflate the variance calculation simply by scaling the vector. The desire to capture the most information is now locked into a strict constrained optimization problem, entirely governed by the covariance matrix. To solve a constrained optimization problem like this, we turn to the Lagrangian method. We construct the Lagrangian by adding a penalty term for the unit length constraint to our variance objective. Taking the partial derivative with respect to B1 and setting it to 0 isolates the maximum, yielding the equality SB1 equals lambda1 B1. This final formula is the exact definition of an eigenvalue decomposition. The math proves that B1 is an eigenvector of the covariance matrix. It represents the absolute best directional axis for projection. The Lagrange multiplier, lambda1, is the corresponding eigenvalue. Its numerical value equals the total amount of variance successfully captured along that exact axis. The covariance matrix dictates how the data space physically stretches and warps. The eigenvector traces the precise direction of maximum stretch. We define this optimal eigenvector as the first principal component. The perfect axis of compression is not guessed or approximated by an external algorithm. It is an inherent, derived structural property of the dataset's own covariance matrix. Extracting a single axis is rarely enough. To capture sufficient detail, we need an m-dimensional subspace, which requires calculating the second, third, and fourth optimal axes. To find the next component, we perform a process called deflation. We take the original data matrix and mathematically subtract the variance already captured by the first component. The algorithm evaluates this newly flattened residual data to locate the next distinct axis of maximum variance. A covariance matrix is perfectly symmetric. According to the spectral theorem, this symmetry guarantees the existence of a complete, distinct set of orthogonal eigenvectors. This ensures every subsequent principal component sits at a perfect right angle to the others, forming an exact orthonormal basis for the compressed space. PCA sequentially constructs a completely ordered orthogonal hierarchy of the dataset's most dominant features. We can apply this ordered hierarchy directly to our 784-dimensional MNIST benchmark. Extracting the eigenvalues specifically for all instances of the digit 8, a clear pattern emerges. This line chart maps all 784 eigenvalues from largest to smallest. The resulting spectrum is incredibly skewed. The curve drops violently. This rapid decay toward zero proves the vast majority of the image's structural variance is tightly packed into just a handful of primary eigenvectors. This allows for an aggressive truncation step. We select only the top m eigenvectors and completely discard the massive, low-variance tail, achieving extreme compression while retaining the core visual structure. The process refines a bloated 784-dimensional space, passes it through the exact calculations of the data covariance matrix, and reduces it down to a tight grouping of pure geometric variance. PCA relies on the rigid laws of linear algebra to guarantee the most mathematically efficient linear compression of reality possible.